Hello everyone, in the lecture today we will start a new topic, traffic loading and volumes. We know that in the road pavement design, traffic is one of the most important factors we have to consider. The consideration of the traffic should include the loading magnitude and configuration, and also the number of the repetitions, which will be the volume. We will discuss both contents in this topic. Generally on roads, the traffic loads from trucks are much higher than those from passenger cars. This indicates that the design of the road pavement should focus on the consideration of the truck traffic instead of the passenger cars. In that sense, it's very important for us to know the distributions of the traffic loads applied to one truck. This one is highly related to the configuration of the axial groups applied to trucks. In this figure, we have one example about a truck with three different axial groups. The first one is a single axial, single tires, where there's only one axial with two tires. The second one is a tandem axial, dual tires, where there are two axials close to each other, and each one contains four tires. The third group is trident axial dual tires, which is applied at the end of the truck. In this group, there are three axials close to each other, and each one has four tires. Actually, depending on the number of the axials in each group and the number of the tires applied for each axial, we can define 5 different axial groups. The first one is a single axial with dual tires, and the second one is a single axial with single tire. Third, tandem axial with dual tires, and we have the trident axial with dual tires. Also, there will be some other axial groups. Traffic loads can introduce a lot of stresses and deformations to road pavements. There are actually a lot of factors affecting the impact of the traffic loads. The direct factors include gear configuration, the tire spacing, the load applied to each tire, and the tire pressure. Also, there are some indirect factors such as pavement design, vehicle type, speed of the vehicles, volume of vehicles, frequency of each vehicle type, and lateral wonder of vehicles. There are actually 3 different procedures for the consideration of the traffic load. The first one is based on fixed traffic, where the thickness of the pavement is governed by a single wheel load, and the number of the load repetitions will not be considered. If the pavement has multiple wheels, then they will convert to equivalent single wheel load, ESWL. This procedure is widely applied for airport pavement or highway pavement with a heavy wheel load but light traffic volume. The second procedure is a fixed vehicle, which is actually one state-of-the-art practice method. In this procedure, the thickness of the pavement is determined by the number of repetitions, and the repetitions is measured in the standard vehicle or axial load, usually is set as 18 kilopound or 80 kilonewton. And this one is just defined as ESAL. Here ESAL stands for the equivalent single axial load. This procedure is widely applied for most of the current pavement design. The last one is called a variable traffic and vehicles. In this procedure, both traffic and vehicles are considered individually, and the load will be divided into a number of groups. Then, the stress, strain, and deflection under each group will be determined separately. This procedure is widely applied by the Portland Cement Association. Now let's first set the equivalent single wheel loads, ESWL. Here the equivalency is cited for stress, strain, deflection, or damage parameters. In the rest of this lecture, we will focus on the estimation of ESWL based on different traffic conditions. Actually, the estimation can be based on the theoretical calculation or experimental results. but there are some criteria we have to follow, including the vertical strain at the top of the subgrade, tensile strain at the bottom of the asphalt concrete, equivalent maximum vertical stress at a predefined depth, and equal maximum vertical deflection at a specific depth. We will go through them one by one in the rest of this lecture. First, let's check the estimation of ESWL with the equal vertical stress criterion. In this criterion, we assume that the ESWL varies with the pavement thickness. The figure below shows the distribution of the vertical stress applied at the different thickness of the pavement. In this figure, little d is the inner spacing between the two tires. Capital SD represents the distance between the center lines of these two tires. And PD is the load applied to each tire. So the total load applied is 2 PD. From the figure, we can see that when the pavement thickness is less than half D, then the stress will not overlap with each other. In that sense, the ESWL will equal to the load applied to each tire, that is PD. If the pavement thickness is higher than 2 SD, then the vertical stress will actually totally overlap with each other. In that sense, ESWL will be 2 times PD. And for the thickness in between, we will have some linear relationship to identify the values of ESWL. The figure here shows the relationship between ESWL and the thickness of the pavement in the log scale. From the previous figure, we know that when the thickness is less than half D, then the value of ESWL is always PD. When it's larger than 2 SD, then it's always 2 PD. For the thickness in between, we will apply the linear relationship, but they are all applied for the log scales. Then with this relationship, by setting one thickness Z, we can find out the value of ESWL P from this figure. We can also simply apply the equation here for the estimation of ESWL under different pavement thickness. This equation is actually applied to describe the linear relationship in the previous figure. So it's only applied for the condition when this pavement thickness is larger than half D and smaller than 2 SD. In this equation, PD is the load applied to one of the dual tire. Z is the pavement thickness. D is the clearance between the tires and represent the inner spacing. SD is the center-to-center spacing between the dual tires. Let's check one example to see how we can estimate the ESWL based on the equal vertical stress criteria. In this example, we assume that there's a set of the dual tire with a total load 2 PD of 9,000 pounds and a contact radius as 4.5 inches, and the center-to-center tire spacing SD is 13.5 inches. It wants us to find out the ESWL for the 13.5 inches pavement. The figure below shows the structures of the pavements and the load applied to the pavement. Now let's check the solution of this example. First of all, we know that 2 PD is 9,000 pounds, which will give us the value of PD as 4,500 pounds. Also, we know capital SD is 13.5 inches. And as we are given the radius of the tire, A is 4.5 inches. Then we can identify the inner spacing little d as SD minus 2 times A, that is 4.5 inches. In addition, we are given the thickness of the pavement as z equal to 13.5 inches. With this information, we can actually find out half d is 2.25 inches and 2sd is 27 inches, which would be the two boundaries for the linear relationship. And then we can draw the line for the ESWL and the pavement thickness as we show in the figure on the right. When the thickness is 2.25, then the ESWL will be 2.5 kilopounds. And when the thickness is 27, then the value of ESWL would be 9 kilopounds. We can then draw a line between these 2 points. And we know that the thickness is 13.5 inches, which can give us the value of ESWL as 7.4 kilopounds. That's one way for us to find out the solution. We can also call another solution based on the equation we defined previously. So we have log ESWL as log PD plus 0.301 log 2z over d divided by log 4sd over d. With this equation, you can find out ESWL as log ESWL as 3.87, which will give you the value for the ESWL as 7,410 pounds, which is very similar to the value obtained from the figure. The estimation of ESWL can also be conducted theoretically with the PoissonAsk theory. In this theory, we want to estimate the vertical stress factor sigma z over q. And with this factor, we can estimate the ESWL with the equation here. In this equation, PS is the single wheel load, which is the ESWL that we want to estimate. PD is the load applied to one of the dual tire. QS is the contact pressure under the single wheel, and QD is the contact pressure under dual wheels. Actually, for the PoissonAsk theory, we want to identify the points with the maximum stress. However, for the dual wheels, we don't know where the maximum stress point it is. In that sense, we need to identify 3 points and on the specific depth z. Here, point 1 is under the center of one tire, and point 3 is under the center of the two tires, and point 2 is actually midpoints between 1 and 3. With the PoissonAsk theory, we can identify the stress at these 3 points, and then the one with the maximum vertical stress factor will be selected for the equation to estimate the ESWL. Let's take the example 1 to see how we can use PoissonAsk theory for the estimation of ESWL. With the PoissonAsk theory, we can estimate the stress factor under the 3 points 1, 2, 3 with respect to the left wheel, right wheel, and the total value, which would be the dual wheel. For the implementation of the PoissonAsk theory, we first need to identify the value of sigma z over qd and sigma z over qs, which would be the maximum stress factor under the single wheel and dual wheel. First, for the dual wheel, which we will need to call the 3 values here. The maximum value is 0.179. And then for the single wheel, well, we want to find out the wheel which will be on top of the points that we want to estimate, which is the tire above the 0.1. That will be the 3 points here. The maximum value is 0.143. Then we can estimate ESWL as, which is also QPS. That is sigma z over qd divided by sigma z over qs times pd. It gives you the value as 0.179 over 0.143 times the value of PD as 4,500. The result is 5630 pounds, which you see is much smaller than 74 and 10 from the previous estimation. Here we can see that the one from the linear relationship is much higher than the one from the PoissonAsk theory, and it indicates that the one from the previous method is safer than the one from the theoretical method. The field data indicates that the estimation of ESWL with the equal vertical stress criterion is not very safe. So in order to improve the estimation, first Alvin proposed the equal vertical deflection criteria. In this method, they assume that the vertical deflection at a depth equal to the thickness of the pavement is obtained from the PoissonAsk solution. In this solution, the deflection at a single wheel is defined as omega s in this equation. The deflection at the dual wheel, which is omega d, is defined in the second equation. In these two equations, Fs and Fd are the deflection factor for single and dual wheels respectively. Also, with the equal vertical deflection criteria, we assume that the deflections from the single wheel and the dual wheel are the same. That is omega s equal to omega d. As we know that there will be two constant variables, A and E. They are the same for the single and dual wheels. So we will have the equation Qs times Fs equal to Qd times Fd. Here Qs and Qd are the contact pressure for the single and dual wheels. If we assume that the contact radius, which is little a, are the same for the single and dual wheels, then we can estimate the load applied to the two scenarios. So we say that P equal to Q times A. If we have the same contact radius, Q will equal to pi times A square. And this could be applied for the single and dual wheels. With that, we will have PS as Qs times pi A square, and PD is QD times pi a square. And if we apply this equation in the formula here, we can find that PS equal to FD over FS times PD. And here, PS is the ESWL that we want to estimate. PD is the load applied to one tire of the dual wheel. Let's check one example to see how we can use the Forster and Alvin's method for the estimation of ESWL in the example 1. Similar to the second example, we will have the values about the FS and FD based on the thickness of the pavement. And for the left wheel, we will have 3 FS values at the 3 points. And also we can find out the value of FD for these 3 points. In the estimation of the ESWL, we need to find out the maximum deflection at the thickness defined in the example. So for FS, that will be the maximum value of these 3 points. So we have FS as 0.478. Similarly for FD, we'll get the value as 0.761. With that, we can find out ESWL equal to PS, that is FD over FS times PD. So we get the value as 73.40 pounds. This one is quite similar to the one we get in the first example, 74 and 10. This is just one coincidence. Actually, for most of the situations, the one we obtained based on the Forster and Alvin method should be much larger than the one from the first criterion. The proposed by Forster and Alvin assumes that the pavement is homogeneous and is not appropriate for the layered system. So in order to improve the method, in 1968, Huang introduced a layered theory for the estimation of ESWL. In this method, we can estimate ESWL from the chart below. This chart shows the relationship between load factor L and the thickness of the pavement. And here the load factor is defined as the total load over ESWL, which would be 2PD over PS. Also, to identify the appropriate line and value of the load factor, we should know the contact radius. The pavement thickness. The modulus ratio. Here E1 is the modulus for the top layer and E2 is the one below. And the dual spacing. Basically, by giving one value of A and SD, we will have one figure. The 2 figures below shows 2 different well spacing and contact radius. The one on the left with SD equal to 48 inches, A equal to 6 inches, and the one on the right, SD is 48 inches and A is 16 inches. And in each figure, the vertical axis is the load factor and the horizontal axis is the thickness. Also, each line will represent one ratio, that is E1 over E2. by giving the value of the thickness and the ratio. We can identify a line and then find out the load factor. And then we can use the load factor for the estimation of ESWL. From the previous analysis, we know that L equal to 2PD over PS. And also we have PS equal to FD over FS times PD. By integrating these two equations, we can derive that L equal to 2FD over FS. So there is a relationship between the load factor and deflection factor. Moreover, in 1968, Huang only proposed two charts for the estimation of the load factor, which are shown in the previous figure. And these charts are applied for the standard wheel spacing, 48 inches, and two standard contact radius, A equal to 6 inches and 16 inches. For any other contact radius and wheel spacing, the estimation can be obtained by the straight line interpolation. Assuming that we are given SD, H1, and A, which are not the standard values, we will first apply the modification about the radius and the thickness. The modified radius A prime and the modified thickness H1 prime could be estimated by these two equations. And then with the modified thickness H1 prime, we can find out the pavement thickness and the loading factors from the two charts. L1 is from the chart with A equal to 6 inches, and L2 is from the chart with A equal to 16 inches. With these two values, L1 and L2, we can then estimate the load factor by the equation here. We find L1 and L2 from the charts, and also we have the modified radius. Then we can estimate the load factors applied for the specific wheel spacing, thickness, and the contact radius. And then we can apply this value for the estimation of ESWL. Now let's check one example for the estimation of ESWL for a two-layered system. The setting of the example is the same to the example 1, and we have a two-layer system with different modulus of elasticity. Here we will consider two different modulus ratio. E1 over E2 will be 1 and 25, and we want to find out ESWL under these two scenarios. In this example, both wheel spacing and contact radius are not standard, so we first need to modify their values for the contact radius and thickness. In the problem, we know that SD equal to 13.5 inches, A is 4.5 inch. Also, the thickness is 13.5 inch. Then we can find out the modified contact radius A prime as 48 over SD times A. That is 48 over 13.5 times 4.5, which is 16 inches. Similarly, for H1 prime, we have 48 over SD times H. That is 48 inches. Here you can see that A prime is actually one standard radius, as we show in the first chart in the previous pages. So we don't need to do any interpolation for the estimation of the load factor. Then, based on the modulus ratio E1 over E2 equal to 1, we have L equal to 1.22. If it's 25, we have L equal to 1.06. With that, we can find the value of ESWL as the total load over the load factor. So that is 9,000 over 1.22, which will give you the value as 7380 pounds. For the second one, we have ESWL equal to 9,000 over 1.06, and the value is 8490 pounds. Basically, we see that with a higher modulus ratio, the value of ESWL will be larger. The third criteria we want to consider is tensile strain criteria, where we assume that the tensile strain caused by the load from the single wheel and dual wheel tires are the same at the bottom of the layer 1. So here it's very important for us to estimate the tensile strain at the bottom of the layer 1. For the single wheel load, the tensile strain will be equal to Qs over E1 times Fe. Here Qs is the contact pressure from the single wheel load. E1 is the modulus of elasticity, and Fe is the strain factor. For the dual tandem wheels, we will have the tensile strain as capital C times Qd over E1 times Fe. Here Qd is the contact pressure from the dual wheel, and capital C is the conversion factor. With the assumption of the same tensile strain, we will have Qs equal to C times Qd from the previous two equations. And then by assuming that the contact radius of the two types of the wheels will be the same, then the contact pressure is proportional to the wheel loads. With that, we will have the value of ESWL as PS equal to C times PD. The next criterion we want to consider is equal contact pressure criterion. In this criterion, we assume that the contact pressure of single and dual wheels are the same. Also, we can estimate the interface deflection for the single and dual wheels by the two equations here. Omega S is the interface deflection for single wheel. In this equation, we have the little q to represent the contact pressure. Fs is the deflection factor for the single wheel. In the second equation, Fd is the deflection factor for the dual wheel. Also, we have the definitions about As and Ad. As equals to square root of Ps over pi q, and Ad equals to the square root of Pd over pi q. With the same contact pressure, we can also obtain the same interface deflection, which will give us the value as omega s equal to omega d. With that, we can estimate ESWL as PS equal to Fd over Fs squared times Pd. So we just need to identify the two deflection factors Fd and Fs for the estimation of ESWL. There are also some other criterions based on the equivalent contact radius. These criterions will determine a single wheel load with the equivalent radius that would lead to the same response if loaded by the same load as the dual wheels. The equivalent single axial radius ESAR will be estimated by the equation here. In this equation, A is the actual contact radius of each of the dual tire, and S is the center-to-center spacing between the dual tires. So that's all about the lecture today. Thank you very much for your attention. In the next lecture, we'll introduce the other contents in traffic loading and volume.